Nathaniel Shar, who will talk about computer-assisted and computer-generated bijectification of combinatorial theorems.
Okay, thanks. So I'll start with a combinatorial theorem. I'm going to define, I'll define in general, but A sub n superscript r is going to be the sum of binomial coefficients n choose k over k raised to the rth power. So we all know what an superscript 1 is, that's just 2 to the n. And for r equals 2, you may be aware that that's, so an 1 is 2 to the n, an 2 is, unless I'm screwing up, I believe it's 2n choose n. But these are easy. What's not so easy is an superscript 3. Okay, sum of the cubes of the binomial coefficients, and this is sum over all k, so 0 to n. You don't get to limit the sum to some of them, so it has to be all. Okay, so this doesn't have a nice closed form, but it does have a recurrence. In fact, they all have recurrences.
It has a name, the
these are the Fresnel numbers, yes. F-R-A-N-E-L numbers. And Fresnel came up with this recurrence. This was in the 1890s. N squared an3. I'm going to run out of room, I think. It's a fairly complicated recurrence. Plus in a second order. 8n minus 2 squared, 8 minus 2 superscript 3. Sorry. Yeah, that's right. Okay. So we don't know what closed form, but we do have a recurrence, a p-finite recurrence for these numbers. And it would be nice to find a bijective proof of this, but it seems hopeless right away because you've got these horrible things here. How are you ever going to make sense out of that? And so what I'm going to show you is how you could do it with a computer, come up with a bijective proof of this. Now, the bijective proof is not as nice as you might be used to if you were a connoisseur of bijective proofs. There's not going to be some pithy explanation and you're going to see instantly where the 7n squared minus 7n plus 2 comes from. Instead, what you're going to see is that I have a bijection and I feed something from one side in and it comes out as something from the other side. That's what you're going to see. And the computer can do this very easily. And then I'll show you how I made the computer do it.
And there's a way to find that you're not cheating, you're not just listing.
Right, yeah. Yes, although, yes, it's not just listing in some canonical order.
But you can guarantee to the user that you're not cheating, that you have a genuine bijection as opposed to manually listing the input and output
and in a canonical order in this. Well, I don't know what you mean to the user, but if you can look at the way the bijection is generated. It has internal structure, which tells you that it's come up. It actually is a combinatorial bijection. It's not just, I made the list and sorted in a random order and somehow paired them. You could do that because the recurrence is true. Any true expression can be bijectified in some sense, but that would be stupid. Okay, so I'm going to use this screen, so I better turn off the light. And I'm going to start by having Maple generate bijection. It's the Fresnel bijection. And I'm going to choose n equals 6 so that we can do this without too much trouble. And I'm going to be careful not to print this out by accident. If you print it's a very large function. If you print it out, it will probably crash Maple. So I will try not to accidentally do that. Okay, it took about 0.75 seconds to build it. All right, this will take longer if n is bigger because there are more terms in the sum. So now let's try testing it. First, let's see what the input is. And this is going to look like a mess, but okay. So this is telling us that the input to this bijection should be, well, it starts with a plus. That means a disjoint union. So I'm taking either the first thing or the second thing. This whole bit down to here is the first thing, and then this is the second thing. So you have to choose one of those. So then let's say we chose the first one, then I have a star, that means a Cartesian product. So I take the Cartesian product of, okay, it's another star, that means the Cartesian product, and then I have 6 and 6. Now 6 is shorthand for this set with 6 elements. 1, 2, 3, 4, 5, 6. So I have 2 elements from that set, Cartesian product, so it's take one and take another, and then a disjoint union of all these things. And you can see that each one of these is 3 binomial coefficients. Now what do I mean by binomial coefficient? Well, this is shorthand for the set of vectors of 6 elements, each 0 or 1, and exactly 5 of them are 1s. And so on for all the others. So that's what input expects. And notice there's another term here. That's because I've actually moved one of these terms to the other side just to avoid having to deal with minus signs. But it doesn't matter, it's still the same recurrence. So we'll start by plugging in one of these, and I'll let you choose which one. So I'm taking a risk here. This bijection better actually be defined on everything, because I'm going to let you choose which one I give it. So, okay, somebody give me a number between 1 and 6.
4.
4. Okay, another one. It doesn't have to be different, it could be the same.
4.
4. Okay. See, I had that, I knew you would do that. Okay. And now I need a number between 1 and 6, because I have to choose, 0 and 6, because I have to choose. Okay, 4. Okay, so now I'm going to pick 3 lists, each of which has 4 1s and 2 zeros. So somebody give me one of those lists.
1, 0, 1, 0.
1, 0, 1, 0, 1, 1. Okay, another one.
The zero's in the front.
Okay, I heard the zeros in the front very loudly. Okay, and one more?
Zero's in the middle.
Zeros in the middle. Okay, now I'm going to try and enter this in. So I'm going to use this function bijeval. I don't know if you can, yeah, you can see it at the bottom. And I want to evaluate bijection B. And now when you have a disjoint union, you need to give it a hint as to which set the thing comes from. Because in this case they're different, but in general they could be the same when you take a disjoint union. You could take the disjoint union of a set with itself, and it would have to be given a hint to know which copy of the set it meant. In this case we're coming from the first set, the one at the top here. So I'll give it a hint by saying 1. And then, okay, we have a Cartesian product, and the first thing in the Cartesian product is 4, 4. That's because we voted for that. Okay, what's the second thing? Well, we have a disjoint union again, so I have to give it a hint. We chose that it would be this term of the disjoint union, which is actually the 5th. So I'm going to give it a hint 5, and now I have a list of 3 binomial coefficients. And each of those is a list, and the first one is 1, 0. The second one is 0, 0, 1, 1, 1, 1. And the third one is 1, 1, 0, 0, 0, no, 1, 1, 0, 0, 1, 1. Did I write that correctly?
Yes.
Okay. And now I have to close the parentheses. And I have to warn you, there's a high probability that I entered something wrong and bewildering error messages will appear. This software is not quite ready for production. The error messages don't yet make any sense. But if all goes well, you won't see any error messages. You'll just see an output. Okay, we win.
Yeah.
But it's really boring. So you chose a very bad example, because all I did, it looks like all that happened was some elements, like the last elements was chopped off of each one. Okay, so I'm going to store that. I'm going to call it output. So I so I get the output so that I can remember it, because I'm going to have to prove to you that it's actually a bijection, that you can go backwards. So in order to be a bijection, it has to have an inverse. So let's see what the inverse, what kind of argument the inverse takes. So, okay, this is what the inverse takes, and as you can see, this is, the first one is this, but I've written 7n squared minus 7n plus 2 in a slightly different way. I've got a 5 times 6 plus 2 times 5 times 5. So it's just n times n minus 1 plus 2 times n minus 1 squared. Is that right? No, that's probably a 6. Or wait a second. Have I not shown you the whole? Oh, there's the 6. Okay, and the other term comes. The other term is No, wait a second. I haven't shown you the whole thing. That's the problem. So that one's. So this middle one is from the second term, and there's more up here, which comes from the first term. And here's another part of the first term. Okay, it's in a bit of a funny order. But this, what we got output, is from the first one here, because it gives the hint 1. So now I'm going to try and go backwards. So I'm going to evaluate the inverse of b at output. And if all goes well, we will get back the thing that we put in. And I really hope this works, because it would be really embarrassing if it did not. Looks like it worked. Okay, so I proved that this is a bijection. Okay, not really. So now the rest of what I'm going to do is explain how the computer does this, and hopefully by the end I'll convince you that if I did everything right, this is actually a bijection and not just me waving my hands at it.
Not to prove the bijection, need to go the other way too. The composition the other way. I'm willing to buy.
Okay, but I already proved to you. Oh, you're right. I would need to go the other way, because I proved to you that it is defined on the first set. But okay, if you believe the Fresnel recurrence, then you believe it's a bijection. Okay, if you believe that the two sides are equal, then you should be convinced. Otherwise, I do need to prove the other way. But we've already proved the Fresnel recurrence, or Fresnel has proved it. We haven't. He has. And so you don't need to be convinced of that. But all right, I just want to show you one more thing. If I picked n equals 6, but it can actually handle much larger n. It takes some time, so this will take, and I'm not going to print this one out, for sure. This will take a few seconds, and it will eventually produce the bijection, and I won't plug anything in because I don't think I have time to ask you for a list of 80 elements. But it will work just fine. So, okay, it's done. It took about 10 seconds. And it seems to be roughly linear. So, and by the way, if I plug something in, it will run just as fast as this one. It's instant. So, I'll now raise the screen somehow. Okay. And how do I make the computer stop displaying?
Go to power, go back to the desktop, and there's a power bar at the, or controls at the top right.
At the top right. Oh.
There should be a power button.
At the top right, like here.
Yeah.
I don't see anything there. Oh, right click. Okay, thanks. All right, so I'll demonstrate how I came up with this, how I made the computer come up with this bijection using a much simpler example. This is a very complicated recurrence. I will now show you a very simple recurrence, but the principle is the same, and a simple recurrence is going to be, I'm going to let an equal n squared. And of course this has the recurrence an equals a of n minus 1 plus 2n minus 1. Let's see if that's right. N equals 2. 4 equals 1 plus 3. Yeah, that's right. Okay. So we all know the famous proof without words of this fact, which is you divide, let's see. You divide your square like this, and then you shade this part, and this is n minus 1 squared, and that's 2n minus 1, so you're done. And the bijection I'm going to come up with is actually going to be the same as this, which is nice. That means that we're doing something right. And on the other hand, this is basically the only reasonable bijection you could possibly come up with. Modulo rotating or flipping or something. And the way we're going to do this is we're going to start by proving this algebraically. So, does this go up or not? It does. And this is extremely interesting and difficult, and I'm sure you will all be very entertained. So I have n minus 1 plus 1. I'm just simplifying n, complexifying n, I guess. And now I'm going to multiply it out. I get n minus 1 squared plus 1 times n minus 1. I'm being maybe unnecessarily careful here, but it'll come in handy later. Plus n minus 1 times 1 plus 1 times 1. Okay, and now I can simplify that a little bit. I get n minus 1 squared. This is already in the answer, so we better just keep it. This is n minus 1, this is n minus 1, and this is 1. And now if I add all those together, I get n minus 1 squared plus 2n minus 1, and I'm done. Okay, all I need to do to get that is to substitute an in the appropriate places, and that's just a name. So I'm now going to show you how you can transform this into a bijective proof. And I'm going to do it like this. I'm going to erase the Fresnel recurrence. We don't really care about exactly what the recurrence is anyway. And I'm going to draw a picture, and the picture starts with the left side of the bijection, which is n squared, which means I have the product of n with n. And I want you to imagine that these are maybe conveyor belts in a factory, and I'm going to put a huge big factory machine on the factory floor, and what's going to come out is going to be this side, i.e. either this or that. So the first thing that I did in the proof was I broke up n in this ridiculous way into n minus 1 and 1. So I'm going to have a machine here, and I'm going to call it sigma inverse because it's the opposite of a sum. It's unsumming it. And breaks it up into n and 1. And I have another machine that's exactly the same here that breaks it up into n minus 1 and 1. And I'm sure you believe that this is a bijection and it's completely routine. Like, I take the set, this is really the set square brackets n, but I'm not going to write that for clarity. And I'm sure you could believe that I can find, in a very routine way, a bijection between this set and the disjoint union of those two sets. And I'll use the same one here. And now, what did I do? I distributed. Okay, this is much more complicated, and it's going to look like a total mess, because it is. Really, there are two distributions going on here. First, I distribute this one across that, then I distribute the other one. So, I should also remark that these are additions, and this is multiplication. I'm leaving out a bunch of parentheses. And so distribution looks something like this. So I have n minus 1 times this plus this. Let's see, which way am I distributing here? Yes. And then that's plus 1 times this plus this. So keeping the labels here so we don't get lost too much. Okay, now I want to do more distribution. I have this times the sum of these. So I would like that to turn into this times this plus this times this. So this is a times, that's a times, and here I still have n minus 1 times n minus 1. Here I have n minus 1 times 1. And then I'm going to do a similar thing here. So and this is 1 times 1. So now I have something, and these are still being added, so I have now something that looks like this. Now the next thing I did was I got rid of the 1s. So I guess I should say here I have a machine which I'm going to label distribution, and it's either right or left distribution. I can't be bothered to figure out which. And this is the other one. So I've now added 3 more machines, and these machines again are pretty routine. All I do is, okay, I get into this machine, I get this and one of these, and I take whichever one of these it is and put it with that. Very straightforward. So these are completely routine. The computer can easily design these once I tell it what the inputs are. Just like these. So these are very routine parts. Now I'm going to get rid of all the 1s. I'm going to call it E for elimination. And again, this is a really routine machine. I give it in anything and a member of the set of one element, and I just throw away the member of the set of one element because it's redundant information. These conveyor belts keep going. Here I have another elimination, and here 1 times 1 is 1, so I have another elimination. Okay, now I need one more machine, which is this step where I added 3 things together and got 2n minus 1. Again, completely routine. Here it's a sum. And out comes something from this set. So I have n minus 1 times n minus 1 plus 2n minus 1, which is the right-hand side. So this big, complicated machine produced the bijection that we want. And you can see that each of these boxes is individually a bijection, and I've hooked them together in a legal way, so the whole thing is a bijection. And that's a proof with, I don't have quotes large enough, proof that it's a bijection.
Maybe the world's most complicated proof of this identity.
Yes, this is the world's most ridiculously complicated proof of this identity. And I did get the computer to do this. And of course, the computer can do this very easily. And again, the function that it prints out, if you try to print out the function consists of, well, in this case, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. What I did on the computer, there are a few more. I've brushed some issues under the rug here, like exactly how many elements are in each disjoint union, because it's not necessarily clear what I mean by this. I could mean there are 3 options, or I could mean something like, so these could be considered different sets, in that here I give it, I say, well, it's either the first or the second, and then if it's the second, it's either the first or the second. Here I say it's either the first or the second or the third. So these are different objects, and here I have 3 things, so I get that exact situation. And so more boxes are required if I'm doing this carefully, to go from one of these to the other, make sure that everything works out. So there are actually 17 boxes when I did it on the computer. So, and each of these, in the implementation I have, each of these is to call all of these functions requires recursive function calls. So there are 17 recursive function calls being made. It's wasteful, but we have fast computers these days, so nobody cares. And as you saw, the Fresnel bijection, which has well over 100 boxes like this, ran instantly. So now I'll show you a little bit more of how this works. So this is the idea. You just if you want to prove something, first you do some algebra like this, and you do steps that the computer can easily replicate with these boxes. So here I did distribution, I did addition, I did canceling a 1, I did addition, and the computer has no problem with any of those. It's easy to make those mechanic. So I'm going to give you a proof. I'll probably skip some parts, but I'll give you a proof of Fresnel's recurrence that uses only boxes that can be mechanized in a similar way. Now, because it has binomial coefficients, I need a few more boxes than I had here. So I will they make these out of lead. Really heavy. Okay. So I'm first going to describe the kind of boxes that I need. These kinds of simple machines. One of them is this. N choose K. It's a bijection that implements this identity. And all I do here is I have a string of zeros and ones, and I flip it. Okay, basic symmetry bijection. Again, I want to emphasize this doesn't. You have to have some creativity to come up with this bijection. But once you've come up with it, the computer can do it. You don't have to think to apply this. Okay, the next one is Pascal's identity. N choose K equals N minus 1 choose K plus N minus 1 choose K minus 1. And again, bijectifying this may require some creativity, but once you've done it, you don't have to think about it anymore. And there's actually more than one way to bijectify this, so you just pick one. And the choice will affect how nice your final bijection is, perhaps. So what I do is I look at the last one, and if it's a 1, then, so I just cut off the last one, and in this case, I ended up here because it was a 1. If it had been a 0, or let's make it this. Draw it. Then I end up here because I cut off the 0. So I did not reduce K in that case, I reduced K in this case. Okay, so that's Pascal's identity bijectified. And then I have one more which is more complicated, that if you want to bijectify any of the Fresnel recurrences, and I mean for r greater than 3, sum of fourth power of binomial coefficients or whatever, this one will come in very handy. And so I should actually, I'll say this is number 1, number 2, and number 3 is this funny identity. Okay, so it's not immediately clear how to bijectify this. It's a little bit more work than those two, but there's a pretty nice bijection. I will skip it for now because there's a limited amount of time. But if you try to come up with one, it's not too hard. It's a simple exercise. Oh, I can't move this. Okay, well I won't move that then. Just go over to the other end. Okay. So now I'll show you how I use those to prove Fresnel's recurrence. Let's get this down.
So these are the macros that the human had to do.
Yes. So the human had to invent these bijections. Although, if I broke this down a little further as n factorial over k factorial, n minus k factorial or something, perhaps a similar approach would get the computer to come up with those.
And in principle, a computer could do everything.
Yes, in principle, a computer can do everything because we are computers and we can do. Well, in principle, a computer can do everything we can do.
Yeah.
That doesn't mean it can do everything. All right, so for this one, I'll define already called this an3, but I'll call it capital AN. And that's going to be the same sum of the cubes of binomial coefficients. And I'll also define an auxiliary function, b of n. This is just a name. Don't worry about it. We'll get rid of it eventually. And that's going to denote a similar sum of product of 3 binomial coefficients, but one is displaced by 1. And now you can, given that I have Pascal's identity up there, you can probably see how this is going to work. I take an, which is the sum of n choose k cubed, and I apply Pascal's identity to each one of these. And I get n minus 1 choose k plus n minus 1 choose k minus 1, and all of this is cubed. And then I just expand it. I get a bunch of things that look like this, or maybe the k's and k minus 1s are switched. So I get a n minus 1 choose k cubed plus n minus 1 choose k minus 1 cubed. I'm taking the terms, the first and last terms first, and then I'll do the rest on the other way. So I have 3 times, and this is all still inside the sum. N minus 1 choose k squared, n minus 1 choose k minus 1 plus n minus 1 choose k minus 1 squared, n minus 1 choose k. 1 parenthesis. Okay, and now notice that that because I'm summing over all k, it doesn't really matter whether I have k or k minus 1. And in addition, if here it does matter, but if I use symmetry, I can flip them. And so this is really just bn, and that's really just an. So notice that I have to use symmetry here. That's why I had to write it down over there. I'm using it as a macro here. So I get 2 times n minus 1 plus 6 times b of n minus 1. Okay, so I found a recurrence for an, but unfortunately it has this thing in it. So do the dumbest possible thing, which is now just try and find a recurrence for b of n and hope, okay, maybe we get c of n, and just hope that this eventually terminates. So this part, by the way, the computer will not do. This part you do as a human, and then you tell it to the computer, and the computer will do the bijection. So you do it for b of n, and yeah, I'm not going to put you through this. What you do is quite similar, except first, so I'll do the first step just to show you how I use that funny identity. So,
and you will have to use something like that as with constant coefficients. You need to get.
Right, I have to use something funny to get the polynomial in there. Because I know there's a polynomial in the final answer, so I have to somehow use something with polynomials outside the binomial coefficients. Good point. So you know that there's something's going to have to happen. So this is the sum of n choose k squared n k minus 1. And now, notice that I have an n choose k and an n choose k minus 1. All I'm missing is an n plus 1. So I will just add it. So I can make the recurrence with whatever coefficients I want. I can add an n plus 1 if I want. Okay. And now I can use that identity. And I get, I can take the n out of the sum, I guess. I don't need to, I'll use it eventually. So, n choose k, n minus 1 choose k minus 1, and n plus 1 choose k. And I guess I combined it with the second one of these. And again, when you're doing this by hand, the order doesn't matter. You can easily see in your head that these commute. When you're doing it with the computer, the computer has to be told, okay, commute these two now. So any commutations can actually radically affect the answer. In fact, the implementation of this I have on the computer doesn't quite get the right bijection out. It doesn't get the one we built that was nice. Instead, if you feed in something that doesn't go to this, it actually flipped the terms. And the reason it did was because I had an additional commutation in there somewhere. Doesn't matter, still bijection. So here's how I used that identity. And as I will skip, like I said, I will skip the rest of the steps, but eventually I have to use it again, so I actually need to add another n plus 1, so I'll just go back and add it. All right. And eventually you get the following. After a bunch of this, I use Pascal's identity again and expand a bunch of stuff, and you eventually get something like 5n squared plus 3n bn minus 1 plus 3n squared plus n a n minus 1 equals b of n. And this is nice because I didn't have a c of n or any other additional auxiliary term. I'm just done. So now I have basically a system of two recurrence equations. And as we all know, you have a system of two recurrence equations, you can convert that into a second order recurrence. But that's not bijective. That's just a statement about algebra. So we have to do this carefully and in a way that the computer can reproduce. So, okay. So what I will do is, okay, first of all, I did all this work and now I'll do it again. And this is, once you've made the computer do the first part, you can very easily do this, because all I did was change n, and I want to do for any n anyway. So I come up with this equation, and also this one. So, oh, wait a second. This is wrong. It's actually n plus 1 squared times bn. I remembered I multiplied by n plus 1 squared, so I should have an n plus 1 squared. And so if I subtract 1 from that, I get the following. Uh, 3n squared minus 5n plus 2, and now you're beginning to see where some of these weird polynomials come from. They come from subtracting 1 from these relatively nice ones, which come from doing a bunch of stuff with that. Okay, so now I'm going to just multiply both sides of these equations by things so that I can use Gaussian elimination. What do I mean by multiplying both sides of these things by something? What does that mean in terms of bijections? Well, if I have bijection that implements this, taking this set to this set, then I can also very easily have bijection that takes, if I multiply this side by some new set, S, which has some size, I just take an element of this and an element of this and map it to an element of this and an element of that. There's a very routine way to do that. I just don't change this element. Okay, so multiplying both sides of an equation by something is another mechanical process. This is not quite the same as before. This is not a box that I run things through. This is, I had a bijection between S and S, and I had a bijection between A, n minus 1, and this thing, and I sort of multiplied the two bijections together. So this is a little bit different, but it's still a very routine thing. In this case, S is going to be, I want to make things cancel, so it should be I want to really get rid of this bn minus 2 because that doesn't appear in the final product. So I'd like it to be 5n squared minus 7n plus 2 and 5n squared minus 7n plus 2. And I will multiply this one by 6. Again, a routine process to multiply something by 6. And now I will add them. Did I do them the right way around? Yes. No. I want to reverse one of them and add. Well, turning it around, that's inverting bijection. That's a routine process. So, and then I add them, and then something very special happens, which is that I cancel this with that. And I'll show you how that works. That's sort of the trickiest thing here. And that gets rid of the bn minus 2. And if I want to show you how the cancellation works, I probably shouldn't do the rest of the algebra. I just want to show you that you can do this kind of linear algebra. And it all uses the same steps of multiplying things and adding things. So this is all actually routine too.
And the computer does it.
The computer does this, yes. So you tell the computer what to do, and it eventually comes up with the recurrence, which unfortunately looks like this. So I'll put a dot, 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 and you get n squared a(n) plus 2, 5n squared minus 7n plus 2, a(n) minus 2 equals 2n squared a(n) minus 1 plus 6, 3n squared minus 5n plus 2, a(n) minus 2 plus 5n squared minus 7n plus 2, a(n) minus 1. Okay, so there's something bad happened. We have one of these a(n) minus 2 terms on the other side. You saw that before when I showed you the bijection on the computer, that one of the inputs could be like this instead of nice and clean like this. But it doesn't really matter. All you have to do is look at this, and you can see that if you subtract it, that you can that you can subtract this, and it will cancel with some of this, but not all of it, and you'll end up with a term on this side. And you can check that that's the Fresnel recurrence. Don't do that. Don't actually, but it is. So modulo a subtraction, this is the Fresnel recurrence. And all the steps I've used to produce it, there was a bunch that used these identities, these bijections, and manipulated them in routine ways, and then a bunch that used linear algebra and manipulated bijections in routine ways. So in the end, I did a whole bunch of routine manipulations of very simple bijections and came up with this monster. Okay. So now I'll tell you the last secret ingredient. I have 4 minutes, but I might be able to do it in this time. The last secret ingredient, which is how to cancel things. We used that step exactly once in this argument. You would use it again if you really felt the need to subtract one of those from one side. And this is the ugliest step in the whole proof because it's the most complicated. And as a result, the bijection you get may not be entirely natural. But we're not going for natural here. I mean, look at that equation. It's not going to be natural. We're going for
but you can argue that this is a natural recurrence. And
that's true.
That is an artificial simplification.
I suppose you could. Fresnel probably wouldn't agree. So what I'm going to show you how to do is, suppose I have a bijection